Let's continue our discussion with diode characteristics and diode analysis. So we look at a graphical analysis technique, and then we look at a diode model. All right. Okay. Load line analysis. That is the first technique we are going to take a look at. So what is a load line? Here we have a simple circuit where we have a voltage supply VSS, resistor R, and diode D. Now, we have the diode characteristic that is plotted from the diode equation, right? This comes from the diode equation. Excuse me. Now, what is the point of circuit analysis? Going back to the first day of 201. Circuit analysis is the process, the techniques to determine the unknown voltages and currents in a circuit. So for a diode analysis, we are trying to determine the diode voltage and diode current. Now, if it's diode voltage and diode current, we have two unknown variables. To solve for two unknown variables, you need at least two equations. We have one equation, which is from the diode characteristic, and the other equation is from the circuit itself. Okay, and in this case, the circuit is voltage supply VSS and the resistor R. Those are external to the diode. Okay, those are external to the diode. So if we write an equation for the circuit and we plot it graphically, we obtain what is known as the load line. And load line describes the external circuit. It is the constraint, actually not the load line, the operating point. But load line basically describes the external circuit. And the external circuit places a constraint on the operation of your device. Okay. So again, two unknown variables, you need two equations. If you try to solve it graphically, you need two plots. One plot is the diode equation plot, resulting in the diode characteristic. The second one describes the external circuit. The external circuit in this case is the voltage source VSS and the resistor R. And the intersection point of these two plots give us something known as the operating point. And that is the operating point of the diode. Okay. The operating point is the intersection of those two plots. So the solution of those two equations gives us the value for diode voltage and diode current. Graphically, it means that the coordinates of the operating point, actually, let's just draw it this way. The coordinates of this operating point give me the values of the diode voltage and diode current. Okay. So the operating point of a diode, or any device for that matter, is the constraint that is placed on the device by the external circuit. And that operating point could move up and down anywhere on the characteristic. Okay. So how can we find or plot that line? Well, we apply circuit analysis techniques. You can apply KVL, KCL, Ohm's law, any circuit analysis technique to determine that line. And for this circuit, it makes the most sense to apply KVL because we have a voltage right here that is supplying energy to the resistor and to the diode. So if I apply KVL to the circuit, I obtain minus VSS plus VR plus VD is equal to 0. Okay. And therefore, VSS is equal to VR, and I can use Ohm's law to describe the voltage across that resistor as ID times R plus VD equal to 0. Three components. VSS is supplying energy to the resistor and the diode. So voltage here, VSS, must be equal to VR plus VD. Right? The VSS is IDR times VD. Now we have the equation. It's a linear line. We can see it's an equation for a line. So how can we plot that line? Well, because there are still two unknowns, but we know that it must intersect the X and the Y axis at some point. So we can simply plug in values of 0 for VD and ID. If we plug in VD is equal to 0, then we obtain ID is equal to VSS over R. And if we plug in ID is equal to 0, then VD is equal to VSS. And you obtain 2 points. Point A here, and point B here. Okay. Again, this is all to plot the load line. The load line. So this is the equation for the load line. And the intersection point of the load line and the characteristic gives us the operating point of the diode. All right, let's take a pause. Think over that. Let me know if you have any questions. Any questions? Now, in general, the devices would be equal. I mean, very similar. So if you have a diode, it's processed right next to another diode on the same piece of semiconductor material, you would expect them to have exactly the same properties, right? But it is never, ever possible to do so with the manufacturing processes that we have. We cannot control every single device down to the single atom, right? Down to every single atom. It's not possible. So even if you have two devices right next to each other, built at the same time, at the same temperature, even operating at the same temperature, it's never going to be exactly the same. Okay. So there's always a range of values for every single diode, or every single transistor for that matter. Okay. There's always variation. But for the most part, they will be very similar within a certain range of values. Okay. So you could take one diode out from this circuit, plug in a second diode in its place, will have pretty much exactly the same response as you see on here. Okay. All right, let's take a look at an example. So we have in example 1, VSS is given to us as 2 volts, R is given to us as 1 kilo ohm. Circuit is the one that we saw previously. we need to plot the load line and determine the values for VD and ID. So for example 1, if you plug in VD is equal to 0, and ID is equal to 2 volts divided by 1000 ohms, using 0.001 amp or 1 milliamp. Oh, sorry, 2. It's 0.002. If we plug in ID is equal to 0, then VD is equal to VSS, which is equal to 2 volts. As straightforward as that. Make sense? The second example, when VD is equal to 0, ID is 10 over 10,000. And so it's 0.001 amp or 1 milliamp. And when ID is equal to 0, VD is equal to 10 volts. So let's plot these two load lines. Let's say 0, 1, 2, 3, 4, 5. Let's say here. If I say this is 10, 5, 2.5, 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 10. That's diode voltage. That's diode current in milliamps. Diode voltage is in volts. 1 and 2. Line for the first one. 2. 10. Example 1. Example 2. And then depending on the diode characteristic that is given to us, or we would plot it using the diode equation, we can obtain or determine the operating point for that diode. Let's take a pause while you write it down, think over it. Let me know if you have any questions. Do the steps make sense? Does it make sense? Okay. Load line analysis is not restricted just to diodes. We apply it to other devices also, like BJT. We perform load line analysis on BJT amplifiers circuits. We can determine what the output is based on a certain given input. Okay, so we'll look at it again also. We'll encounter it in different chapters. Now let's turn our attention to the first of our diode models, the ideal diode model. In an ideal diode model, which of course doesn't exist, we simply replace the diode with either a short circuit or an open circuit based on an assumption. Okay, we can assume the diode is either on or off, and we can replace it with either an open circuit or a short circuit. Basically, if the diode is forward bias, the diode is on. The diode is reverse bias, diode is off. In order for a diode to be forward bias, the anode of the diode must be higher than the cathode. Okay. So forward bias requires the anode is higher than the cathode, then it's forward bias. If anode is less than the cathode, it is reverse bias. This also means that the diode voltage in forward bias is positive, and diode voltage when it's reverse bias is negative. Remember, voltage polarity is simply indicating what your point of reference is. The value of the voltage doesn't change. A couple of slides ago, I pointed out when we introduced the diode characteristics, I said VD and ID. VD is always taken with positive reference at the anode and negative at the cathode. ID, the same thing, positive the anode, negative at the cathode. Simply stated, if you have a multimeter, if you're trying to measure the diode voltage, somebody says, go measure VD or diode voltage for diode number 3. Well, you would take the meter, the positive terminal of the multimeter would always go to the anode of the diode, negative terminal will always go to the cathode of the diode. That's all it means. Okay, always think in terms of measurement. If you have a meter, positive always goes to anode, negative always goes to cathode. That's the reference. That's diode voltage VD. Same thing for ID. You would break the circuit, you would connect the positive terminal flowing from anode to cathode. Okay, anode to cathode. That's always the reference for current. So if your assumption is that the diode is on, then follows that the diode voltage VD is positive, VD is negative. For an ideal diode, we're talking about ideal diodes, meaning it doesn't require any external potential, meaning as soon as it crosses zero, slight zero, it conducts and it's replaced with a short circuit. So for an ideal diode, because it is replaced with a short circuit, what is VD? Short circuit means there is a wire connecting two nodes. Exactly, it's zero. If there's a wire connecting two nodes, they're the exact same node, meaning there's no difference in electric potential between those 2 points. So the difference is zero. It means the voltage is zero. So VD is zero. So for an ideal diode model, VD in forward bias is zero. In reverse bias, meaning when the cathode is higher than the anode, VD must end up negative. If your assumption is that the diode is off, then the VD value must be negative. In that case, for an ideal diode, ID is equal to 0. No current flows through. It's open circuit. ID, diode current, is equal to 0. And here, let's move this down a little bit. Okay, ID is positive because current is flowing through in a positive diode. So again, replaced with an open circuit. That's your diode VD, and replaced with a short circuit. Current is flowing through. And that's the ideal diode model. It doesn't require any extra voltage for it to be forward biased. Replace with a short circuit or replace with an open circuit. Let's take a pause. Let me know if you have any questions. Yes. Diode is off. That is absolutely correct. VD should be less than 0. Good catch. Let me do a strike through. Yes. So let me see if I understand the question correctly. We make an assumption, and then at the end, VD should be equal to 0, meaning match the assumption of the diode being on. Okay, I get what you're saying. Okay, so this is in general. So the question being asked is about, I first initially stated VD is positive. Now I'm stating VD is equal to 0, right? Okay, it's a good point. Confusing. So this is in general, meaning non-ideal diodes, real life diodes. If you have a real life diode and you forward bias it, then it must have a positive value for VD. So this is real diodes. And which leads me to conclude after that is that if I'm referring to an ideal diode, then doesn't require any voltage, VD is equal to 0. The key point is that it should not be negative. If we assume that a diode is forward bias in a real diode or an offset diode model, it must be some positive number. Remember, silicon diodes require 0.6 volts to 0.7 volts to turn on. So it's positive 0.6 volts plus 0.6, right? In an ideal diode model, we do not take into account that 0.6 volts. We simply say diode is on. So first, we state VD is positive because it's forward bias. But if we use an ideal diode model, we simply state it's 0. If it's reverse bias, that means voltage is negative. And that is true for both ideal as well as real diodes. Does that answer your question? Yeah. All right, any other questions? Okay, let's look at the steps. So if we were to analyze a diode circuit using the ideal diode model, the first thing we would do is make an assumption, whether the diode is on or whether the diode is off. Okay, you make an assumption, and based on our assumptions, we replace the diodes with either a short circuit or an open circuit. Okay, they're short circuit or an open circuit. Okay. And that again goes back to the point that if you're making an assumption, that assumption should be based on certain logic. If you look at a circuit, there might be multiple power supplies in there. There might be multiple diodes in there. If we look at a circuit and we can do a general calculation before we begin an analysis, we can just look at general observation, not even a calculation, that the anode seems to be higher than the cathode, then we should assume that the diode is on. If the cathode seems to be higher than the anode, then we make an assumption that the diode is off. And then we perform our analysis. We replace the diodes with either a short circuit or an open circuit. Once it is a short circuit or an open circuit, all we are left with in the circuit are a bunch of resistors. They are connected by wires. We can apply any circuit analysis technique we want to determine the unknown voltages and currents at any point in that circuit. And once we are done with that, we look at the solution and see if it matches our assumption. Okay, we look at the values that we obtained for the diode voltage and the diode current, and we compare it to the assumptions we made at the top. If it matches the assumption, great. If it doesn't match, then we go back to the top, we change our assumptions, and then we begin all over again. For n number of diodes, we can have 2 raised to n possible states. Not possible states, possible combinations. Okay, if you have n diodes in a circuit, each diode has 2 possible states, so we have 2 raised to n times 2 raised to n possible combinations. One diode, only 2 possible states, on or off, easy to analyze. 2 diodes, 4 possible states, 4 possible combinations of the circuit. Either both are on or both are off, or either one is on or off. 3 diodes, 8 possible combinations. 4 diodes, 16 possible combinations, so on and so forth. So when you are going through your assumptions, again, depending on what we assume, it could be correct, it could be incorrect. If you're lucky enough, or if you're smart enough or good enough to make an assumption, you can have the answer in the first try itself. Personally, I always have to go through a few assumptions before I arrive at the right answer. If it's anything more than like 3 diodes, I have to go through like 4 different analyses before one of my assumptions proves to be correct. Okay, let's take a look at an example. So we have a circuit with 2 diodes, 2 power supplies, and 2 resistors. Okay, D1 and D2, and then 4K and 6K resistors, and 10 volt and 3 volt supplies. Let's just take a few moments and look at the circuit. What do we see? We see 2 voltage supplies, 10 volts and 3 volts. And both of them are connected to anodes of, the diodes, D1 and D2. If I take D1, Generally speaking, I have a 10-volt supply to the anode of D1, and I have a 3-volt supply on the side of the anode, or sorry, on the side of the cathode of D1. Just look at D1, nothing else. If you look at D1, I have 10 volts at the anode and 3 volts at the cathode. What is our logical conclusion of the state of the diode? I hear one on. Anyone else? Are the rest for off? Logical conclusion would be that the diode is on. So I would choose my assumption to be D1 to be on. How about D2? Anode is closer to 3 volts, cathode is closer to 10 volts. So cathode is higher than the anode. So that leads me to conclude that D2 is most likely off because the cathode is at a higher voltage. Okay. So if I use that assumption and I perform an analysis, then I would see what my answer, if my answer matches up with the assumption. But let's just say I go with the silent majority. I go with the silent majority, which are telling me that D1 is off and D2 is on. That's the case. D1 is replaced with an open circuit. D2 is replaced with a short circuit, which is illustrated in figure B. Assumption is that D1 is off and D2 is on. So you replace D1 with an open circuit, D2 is short circuit. If D1 is open, that means it should have a negative diode voltage. You take a multimeter, put it across D1, positive at the anode, negative at the cathode. If it's indeed off, then this cathode should be higher. Cathode is higher, then the measured voltage must be negative. So if VD1 turns out to be negative, that means our assumption is proven valid. So let's get to it. And then, of course, if D2 is on, then VD2 should be equal to 0, and ID2 should have some positive value. So in this case, it's rather simple because we only have one voltage source, 3 volts. I can apply Ohm's law, and I can determine the current flowing through that diode. .5 milliamps. Okay, 0.5 milliamps. Positive value. What does it mean? Diode is on, positive current must flow through the diode. That means my assumption is valid. D2 is on. But that's only half the analysis. Let's look at D1. So we want to find the voltage across D1. So for D1, voltage at the anode and voltage at the cathode. What is the voltage at the anode for D1? There's no analysis required. It's an open circuit. Current cannot flow through. So the voltage, you were saying? Well, current or voltage? Current is 0 because no current is flowing. But if it's an open circuit, left dangling in the air, then the voltage at both ends of the resistor is exactly the same. I is 0, so voltage is exactly the same, 10 volts, measured with reference to the node at the bottom, right there. Node voltage. It's a diode voltage. Anode voltage is measured with reference to the bottom node. Cathode voltage also can be measured with reference to the bottom node. Because it's an open circuit, voltage at both ends of that resistor is exactly the same. 10 volt supply connected at one end of the resistor, meaning if you measure the voltage at the other end of the resistor is also 10 volts. So this is 10 volts, and this is also 10 volts. Voltage across the 6 kilo ohm resistor is, and we don't require any analysis for that, it's 3 volts because it's in parallel to the 3 volt source. So for D1, the voltage across its anode and cathode, voltage at the anode is 10 volts, voltage at the cathode is 3 volts. VD1 is +7, positive voltage, which means my assumption is incorrect. Because my assumption is that D1 is off. If D1, a diode, is off, then the voltage VD, or VD1 in this case, must be negative. If it is not negative, then my assumption is incorrect. Okay, my assumption is incorrect. So let's take a pause. Will you write it down? Let it sink in. Let me know if you have any questions. Assumption is incorrect. Do the steps make sense? The circuit analysis techniques that we apply depend on the problem. Here it was easy. It's a rather simpler or straightforward circuit. So the analysis is straightforward. We did not have to do any other, we did not have to apply any other equation or technique. But depending on the circuit, our techniques and our approach would change. So our initial assumption was D1 is off, D2 is on. D2 was proven to be on, D1 incorrect. But we cannot take only parts of an assumption. Okay. The result we obtain is due to the assumption of both diodes. So we cannot say that the analysis for D2 is correct, so D2 is indeed on. No. Now we have to try a different combination. We could either try both on, or we could try both off. Or we could go with the original intuition or original logic assumption that D1 is on and D2 is off. Okay. Again, this is critical. If you have two diodes, we made an assumption. One of the diodes turned out to be correct. The other one turned out to be incorrect. But that means that our entire assumption is incorrect. We cannot keep the portion that is correct and say that is our final answer. Does that make sense to everyone? right? We have to go back and change the assumptions for all diodes. So out of 4 possible combinations, we tested one. Let's test another one. And in this case, let's test D1 on and D2 off. And for this combination, on means replaced with a short circuit, D2 is replaced with an open circuit, and we obtain from this assumption figure C. Is right there, that circuit. Diode D1 is a short circuit, so we have ID1, VD should be equal to 0, or VD1 should be equal to 0, and ID2 should be equal to 0, and VD2 should have a negative value. ID1 in this case is the straightforward quantity. And so we have 10 volts divided by, this is a series circuit. The right side of the circuit is disconnected. And so this is 10 divided by 10,000. 4 plus 6K. That gives me 1 milliamp, or 0.001 amp. Okay, 0.001 amp. All right, so ID1 is a positive number. My assumption is verified that diode D1 is on. Similar to the first assumption analysis. How about the next one? We need to find VD2. The anode of VD2, or the anode of diode 2, is held at 3 volts. Okay. VD2 is voltage at the anode, which is 3 volts. And what is the voltage at the cathode? So this is anode voltage. What is the voltage at the cathode? Again, we'll do a circuit analysis technique. This right here is 3 volts. And the voltage at the cathode, here 4 volts. Close, but not quite. So it'll be the value of the voltage across the 6 kilo ohm resistor. Make sense? And we can find that or determine that by applying voltage division. Because again, 4K and 6K are in series now. If the circuit is open on the other side, that means nothing is connected to those 2 nodes, effectively rendering 4K and 6K resistors in series. The series connection of resistors, fraction of the supply voltage appears across each resistor. That fraction is voltage across 6K is 10 volts times, let me write it down here. Cathode voltage is 10 times 6,000 divided by REQ, which is 6 plus 4, 10,000. Gives me 6 volts. So voltage at the cathode turns out to be 6 volts. 3 minus 6 gives me a negative value for my diode voltage for diode D2, which matches my assumption that diode D2 is off my assumption is valid. So D1 is indeed on and D2 is off. All right, write it down, think over it. Let me know if you have any questions. If we had chosen both diodes to be off, answer would again be incorrect. If we had chosen both diodes on, it would again be incorrect. So I would strongly recommend or suggest that you do practice analyzing the circuit for the other two assumptions. Okay, both diodes on and both diodes off. Shouldn't take about 15 to 30 minutes, I would say. That would be good practice. Okay. All right, we'll end class here today. Just a couple of announcements. Homework is updated in the system with the due dates. So please keep up with the calendar. You can also access Pearson directly. You can also, it syncs through Canvas also, so you can check in there. The scan homework deadlines, if the due dates for the Pearson homework move, I'll move the scan homework deadlines at the same time, but just in case there's a discrepancy between the Pearson and the scan homework, the Pearson one is the right one. The scan homework is, whenever it gets submitted, it's fine. Friday quiz. Again, not standard would be just doing it on Friday, 1 day extension, but again, deduction if there's a late penalty. Friday quiz will assess material from the previous Wednesday, Monday, and Friday. And then Monday in-class quiz would assess material from the previous Friday, Wednesday, and Monday. Okay, so this Friday's quiz, again, offline. You just take it whenever you want, but it will not be like a 3-day time frame. Only 1 day time frame on Friday. All right, let me know if you have questions. Reach out via email, and I will see you on Friday.